watching this video, and welcome to the workshop on vision applications and solutions to biased or scarce data. My name is Andy Bagdanov from the University of Florence and the Media Integration and Communication Center at the University of Florence, and I'm here today to talk to you about self-supervised learning, or as the subtitle indicates, how to get more for less out of your convolutional neural networks. So a very high-level overview of what I'm going to talk about right now. So first, we'll look at some of the motivations for why we might want to perform self-supervised learning. Then what I'm going to do is I'm going to present three of what I think are pretty illustrative and representative approaches to what is known now as predictive self-supervised learning for visual representation learning. And then I'm going to contrast that with what I like to think of as self-supervised learning applied to niche applications, using a technique developed by myself and colleagues, which we call learning from rankings or learning to rank. It depends on how you think about it. And then, of course, we'll do some reflecting and discussing of what I talked about at the end. Okay, so actually, the first thing that I'm going to do is I'm going to turn my video off so that I can make use of all of the screen real estate during my presentation. So let's get going. Okay, so one of the things that we all know, anybody who's been working in computer vision over the last 7-8 years, is that convolutional neural networks are obviously the model of choice for quite some time now. And we also know, and we're very familiar with the fact that convolutional neural networks are very big in terms of the number of trainable parameters that they have. This is a version of what has become obligatory diagram illustrating the size of a wide variety of state-of-the-art models in terms of number of trainable parameters, in terms of the number of operations required for a single forward pass, and the top one accuracy that they achieve on the ImageNet benchmark. And so this figure is, well, it's aside from being an interesting and useful summary of a snapshot of the state-of-the-art, what we see from this is that if we want to obtain state-of-the-art results in terms of object recognition as represented by ImageNet, we need to use models that have tens, if not hundreds of millions of parameters, of trainable parameters. And of course, we know that having more trainable parameters implies having more annotated data available for training. That also implies performing careful regularization to avoid overfitting, et cetera, but in general, training large models like this was largely made possible by the availability of massive amounts of annotated images. ImageNet, for example, is the commonly cited example. In any case, training models with this many parameters incurs all kinds of costs. So it costs time, it costs money, there's a non-negligible carbon footprint, so on and so forth. This is sort of an accepted fact of life when using modern, large convolutional network architectures. So annotation and large-scale training are expensive. So the combination of these two facts of life is quite expensive. It's expensive, it's laborious, and it's noisy. So let's do some quick back-of-the-napkin calculations using this sort of arbitrary 8-cent number that I found from a commercial annotation service available on the internet. That said that commercial rates for image annotation are about 8 cents per annotation. This is an average of a few different services, if I remember correctly. In any case, if we wanted to annotate 1 million images, let's say, that's a single annotation per image, the ImageNet style. That means that we're going to have to spend about 80,000 dollars. Sorry. So this is sort of an arbitrary calculation, but we can see that this model doesn't scale very well. And image annotation is also quite noisy. One annotation per image, even if that's the target, you only need one class label, for example. Typically, multiple annotations have to be performed so that you can compute annotator agreement scores and arrive at a consensus annotation for every image. And so this 8 cents per image is probably not going to be an accurate reflection of what you're actually paying. Okay, so image annotation is expensive. It's labor intensive because somebody has to sit down and do this, and it's noisy. And the only way to compensate for noise in your annotations is by performing redundant annotations. Or that's the most common way of compensating for noise in your annotations. And one last comment. So this refers to a single annotation, an object category, for example, per image. If you need more costly annotations, for example, object bounding boxes or pixel level annotations for semantic segmentation, obviously this 8 cents per image doesn't hold any longer. So large-scale training, okay, in addition to requiring annotated images to perform fully supervised training, is expensive and time-consuming as well. So even if we have, especially if we have massive amounts of labeled data, if we want to train a state-of-the-art convolutional neural network, that can require weeks of CPU time, depending on how many CPUs you can throw at the problem in parallel. And this is just for a single training run. If we're optimizing hyperparameters for a complex model, obviously we're going to have to multiply this by n. Okay? So you can parallelize a lot of this, but this is clearly limited by the number of GPUs available, energy costs, so on and so forth. Okay, so large-scale, massive data sets, annotated data sets, have made possible training large models like this without severe overfitting. So let's take a step back and ask ourselves what 1.5 million annotations are really worth. So if we have equiprobable labels and we randomly shuffle the set of ImageNet labels, we have, well, about 15 megabits of information contained in the annotations of 1.5 million ImageNet labels, class labels, one class label per object, per image. And so if we compare this with the representational capacity in even a modestly sized convolutional neural network, we see that the amount of information we're providing to learn from is dwarfed by the number of trainable parameters. And so this is exhibited also in these plots here from this excellent paper that I highly recommend, Understanding Deep Learning Requires Rethinking Generalization. And these plots demonstrate how it's possible to fit even randomly assigned labels to ImageNet images eventually. Obviously, it's easier to fit the actual labels, the ones informative to the actual object categories. But even if you do random assignments of labels to images, it's possible to fit the labels eventually perfectly on the training set. So even with 1.5 million labels, it's not really enough to constrain the overfitting capacity of convolutional neural networks. So that's one aspect of the burden of annotation and the worth of annotation with respect to the representational capacity of convolutional networks. But sometimes it might be impossible to annotate massive amounts of data. So I might just not have the number of labeled images that are necessary. Or there might be some problems like open set face recognition or person re-identification where the learning problems are inherently sample limited. So it might be impossible to label images even if I wanted to. So do we have to abandon these highly overparameterized models and go back to classical approaches? Well, we all know that that's not the case, because the true representational power in a convolutional neural network, it's not really in the classifier that is meticulously and laboriously trained using massive amounts of training data, but it's in the convolutional features learned in the earlier layers of the network. And transfer learning, we all know, works quite well for a huge variety of object recognition, image recognition tasks. Okay? So, but in these cases, we're still using a network pre-trained using massive amounts of labeled image data. So in this talk, what I want to do is I want to talk about self-supervised learning techniques, which obviate the need for having massive amounts of task-specific data to learn general image representations. So in the talk, I'm going to first describe a few examples of predictive self-supervised learning, which are contrasted from, no pun intended, with contrastive self-supervised learning approaches, which are sort of becoming all the rage lately. But I'm going to talk about predictive self-supervised learning because afterwards, what I want to do is I want to talk about a specific approach developed by me and my colleagues that's based on learning to rank that we can apply to image regression problems, which can be considered more niche applications. Okay, so in some sense, they're more broadly applicable because if you have a very specific problem and you can design a pretext task, we'll see what that means in just a second, that you can self-supervise, well, then you can learn image representations that are appropriate for your specific task. So this is the pipeline for self-supervised learning that we should all keep in mind when going through this talk today. So the general schema is to train a convolutional neural network on completely unlabeled data, typically massive amounts of unlabeled data if we're doing general image representation learning. But this training is supervised using what's known as a pretext task. Sometimes in this talk I will refer to it as a proxy task because in our papers we refer to it in that way because it's in the end a task that stands in as a proxy for the downstream task that ultimately we are looking to solve. And in this pipeline, after pre-training the network using self-supervision, we transfer the weights into a new convolutional architecture with some task-specific layers, typically, and then we train the network, which can be trained using fine-tuning or just training these new task-specific layers on supervised data, which is typically orders of magnitude less in quantity than the amount of unsupervised data that was used during the self-supervised pre-training. So the first technique that I want to talk about is an appealing approach because it's easy to see how and why the network is being encouraged to learn semantically meaningful or semantically rich image representations. So the idea behind this approach is, well, the title actually gives everything away. Unsupervised visual representation learning by context prediction. The idea is if you have an image and you sample a patch somewhere in the image, and then you randomly sample one of these 8 patches around it, what you can do is you can devise a self-supervised proxy task or pretext task by requiring a network to classify which of these 8 patches the second patch was sampled from. So here we have a couple of examples, and you can see that it's pretty easy for us, because we understand image semantics, to spatially infer which of the 8 patches this patch comes from. So in general, what this does is it forces the network to understand things about object and image semantics. So if it sees a combination of patches like this, the network has to have learned that, well, this is one of the ears of the cat. Obviously, it's not reasoning about ears and eyes and faces, but and the ear of the cat that looks like this is typically up and to the right of patches that look like this. And so the network, should output probably a high confidence classification for patch 3. So the architecture of the network, as in a lot of self-supervised representation learning approaches, is Siamese. So you have 2 branches of the network which share all of their weights. And at the end, these 2 representations for the center patch and one of the randomly sampled contextual patches are concatenated and then fed through a fully connected multilayer perceptron classification pipeline, which outputs 8 probabilities for the 8 possible contextual locations. So one of the things that you always need to be careful about and need to be very, very aware of is the fact that networks can and will cheat if they can find a way to do so. So what do I mean by cheat? Well, in the case of context prediction, in this work, for example, you'll see that these patches are not directly adjacent to the center patch, the originally sampled center patch. They're spatially jittered in order to provide some random variation in the way that they're sampled. Because if you sample directly adjacent patches, well, the network can just use low-level image features like gradients, for example, to determine continuity and infer in which direction the sampled patch comes from. A slightly more subtle example of networks cheating in this work is due to a phenomenon known as chromatic aberration. So one of the things that the authors report in this work is that when they first started training networks using this self-supervised loss, the loss was minimized very quickly, almost immediately, but the resulting image representations were useless. And the reason for this is because CCD sensors suffer from a phenomenon known as chromatic aberration, which, at a very high-level description, causes them to compress the range of green color channel measurements more towards the center of the image. So what happens is when the network is looking at patches in the image, just by looking at the green color channel, you can think of it as sort of a type of a compass pointing in the direction of the center of the image, which allows the network to roughly identify the spatial relationship between two sampled patches. Okay, not perfectly always, but pretty well. So what this translates to is that it can optimize the self-supervised loss without having to learn any semantic information about images in general. And this obviously has to be avoided. In this case, eliminating color information, eliminating the effect of this chromatic aberration was enough to cause the network to rely on semantically rich information to optimize the loss. So when we're performing self-supervised learning, how can we tell if it's working? So if the network is really learning something about semantics? Well, one of the ways to do this is to sample patches from a set of images, compute the fully connected representation learned via self-supervision, and look at nearest neighbors, in this case, the 5 nearest neighbors in the set of patches that you've sampled at random from a large set of images. And then you can compare this to what networks pre-trained using ImageNet labels return. You can also compare it to random initialization. And so here we see, for example, that, well, if you feed in patches with motorcycle wheels, it looks like cat faces, human faces, car wheels. Well, just like ImageNet pre-trained network representations return semantically relevant or semantically similar concepts, the pre-training using this context prediction, self-supervised loss, is also returning semantically relevant image patches. Okay, so this is a qualitative way to understand if self-supervision is doing something that will hopefully be useful for solving downstream tasks. So I wanted to sort of avoid bombarding you with these us versus them tables in this presentation. But at least one of these tables is useful to look at, because what we're interested in understanding is how the self-supervision works compared to fully supervised training of the network. In this case, this is results of an experiment performing self-supervision on ImageNet without using any of the labels, and using the resulting representation via fine-tuning to perform detection evaluated on the Pascal 2007 object detection benchmark. And here we see the difference, for example, between using an ImageNet network pre-trained, a VGG network pre-trained on ImageNet, okay, compared to all versions of this self-supervised training. And so as you'll see, there's always a gap. Okay, because self-supervised pre-training is still chasing after this fully supervised benchmark. Okay, so this is the gap that we want to look at whenever we're trying to understand how well our self-supervised training is working. Okay, let's look at another approach. And this approach is based on the counting of low-level visual primitives. And so the main idea behind this approach, okay, which is called representation learning by learning to count, the main idea is to learn visual primitives, okay, that are learned in such a way that they respect a decomposition property. Namely, that, as you would expect, if you detect these visual primitives, the number of visual primitive occurrences of each of these primitives for the entire image, and then you compute it for the 4 sub-images as illustrated here, well, the sum of the counts of these sub-images better be equal to the counts of the detectors when applied to the entire image. Okay, so one of the things, so again, always be aware that you need to think about how can the network cheat. Okay, so we need to be careful that whatever is being counted, okay, and verified that the counts, when summed over the 4 subregions, equal the counts for the entire image. We need to make sure that this is actually requiring the network to learn something about image semantics. Okay, so let's take a look at how the actual architecture, how does this approach actually work? Okay, so the idea here is that you take an image, you sample a patch from the interior of the image, a large patch from the interior of the image, and then you split it up into 4 sub-patches. Okay, then you send the entire image through the network and the 4 sub-patches through the network. Okay? And if you look at this network architecture, this is just an AlexNet architecture. So in fact, here, as they say, this is AlexNet, the first 5 convolutional layers, and then you pass it through a sequence, the standard sequence of fully connected layers, ending at a 1000 output fully connected layer, just like the original AlexNet, okay, that's passed through a ReLU. Okay? The idea is that these 1000 outputs, each of them is corresponding to one of these visual primitives that we want to count. Okay, so this will correspond. Each one of these outputs will correspond to the number of occurrences of that visual primitive in the input image. Okay, so how is this enforced? Okay, how do we enforce this decomposition invariant that we want? Well, we have passed all of the sub-images through the exact same network. What we do is we sum the outputs, the 1000 outputs of each of these, resulting from each of these sub-images. We sum them together, and then we put them through a squared error loss. Okay, so this guarantees that the sum of these visual primitive counts is learned to be equal to the sum of the visual primitive counts on the entire image. Okay, so how is it that the network can cheat? Well, it can cheat, for example, by always outputting 0 or outputting any constant number, for example, because you're still guaranteed, and a constant number actually would not be the case. 0 would still be the case. But, for example, you could be counting just the effective area of each one of these of each one of these patches in original pixels. Okay, so how can we enforce the network to not output these sort of degenerate solutions? Well, what we can do is we can pass another image through the network. Okay, so we pass this other image, which is going to produce 1000 visual primitive counts in the end. And what we do is we just require that the counts of these visual primitives be different than the counts of the visual primitives in this other image. Okay, so this avoids these sort of degenerate constant solutions that the network otherwise would learn rather easily to trivially optimize the output, to trivially optimize the self-supervised loss. Okay, so again, this type of self-supervised learning is in the paper demonstrated to be useful for a variety of tasks. So classification, detection, and segmentation in the Pascal dataset. So again, what we're looking for is a comparison between the fully supervised approach and the self-supervised approach. So we see that there's still quite a significant gap between these results, but still significantly better than random initialization. Okay, so self-supervision is doing something for us. It's still not as good as having the full supervision, pre-trained supervision using ImageNet labels, but it's a heck of a lot better than doing random initialization and training on the Pascal datasets for all of these tasks. So again, how do we know if we're learning something? Well, we perform this same type of verification. And here we see that, again, if we give an input patch with people in it, well, the other patches with people in it are generally the nearest neighbors. In this paper, I think this might be the first paper where what has become a standard benchmark was first proposed. So the authors of this paper showed that if you take the self-supervised representation learned in the convolutional neural network, use that as a feature extractor, this can be easily repurposed without having to spend a lot of GPU hours fine-tuning the network using a multi-class SVM or logistic regression classifier. Okay, so here we see results of this using counting, learning to count, which works actually quite well using a very simple classifier. Okay, so there's no extra training required, no fine-tuning required. This is known as the linear benchmark, which has become, as I said, a common approach to verifying the representations learned via self-supervised learning. So color is a really strong semantic cue for humans, and perhaps not surprisingly, colorization makes a great pretext task for self-supervised learning. Unfortunately, in the interest of time, I'm going to skip over the details of this. But if you're interested, the video that's uploaded to the website talks about this technique in some detail. The technique is colorful image colorization. And as you'll see, if you take a look at the video, colorization seems to be a pretty good front runner for pretext tasks for general self-supervised learning. So how can we apply ideas from self-supervised learning to what I call niche problems? Okay. So up until now, we're talking about self-supervised learning for general representation learning. Okay, well, what we want are representations like the pre-trained image networks where we have a generically useful image representation that we can then repurpose for detection, segmentation, classification, so on and so forth. But a lot of problems that we might want to solve using convolutional neural networks, well, we don't really want or need a general image representation. Okay, and such niche problems might need more specific semantics. Okay. And so for a lot of these problems, data might be extremely hard to come by. It might be very expensive to annotate, or it might even be impossible. So things like medical image analysis, face recognition, open world re-identification problems, or two applications that I'm going to talk about right now, image quality assessment and dense crowd counting. The image quality assessment is something that most of us probably don't really think about. So image quality is an important metric for a pretty huge array of applications, things like video and image transmission, compression, imagery for advertising. All of these applications have to have some sort of guarantees about the quality of the resulting imagery. And so image quality assessment is exactly this. You get a group of people, you have them look at images, a group of experts, okay? These are highly trained persons that evaluate the subjective quality of images. And of course, this is a subjective measure, and so you have to have lots of experts evaluate them, and you arrive at a mean opinion score by averaging the judgments of all of these experts. So collecting data for this is extremely expensive. So first of all, every expert is an expensive expert by definition, and to arrive at any sort of objective measure in terms of mean opinion score, you're usually going to want about 100 independent judgments per image. Okay? So this is one of the reasons why most data sets available for image quality assessment, at least up until a few years ago, only had a few hundred or a few thousand images in it. Okay, far too few to accurately or to reliably train convolutional neural networks. So how can we use self-supervision to help out? So the key idea, okay, that we had is to use a ranking task as our pretext tasks. Okay, and a ranking task for which we can automatically generate some training signal. And then from that point on, the pipeline is the same as general predictive self-supervised learning. We transfer the weights to a new convolutional network that then estimates the absolute image quality assessment. So an important difference between this and the other approaches to self-supervised learning is that here we're talking about regression problems. Okay, so here we have we're talking about networks that take an image and produce a scalar value. Okay, that should be correlated to this mean opinion score of absolute image quality. Okay, and that's important because in order to define this ranking pretext loss, you need to have some orderable output space, like a scalar output space. Okay, so how does this work? Okay, first of all, we use a Siamese network. Okay, we input pairs of images to the network, each pass through its own branch. Okay, the key to our approach is that we need to construct the batch. We construct these batches in a very specific way. Okay, we construct these batches in a way such that we know for sure the relationship between the quality of this image with respect to this image. Okay, so we know that the quality of this image is higher than the quality of this image, the corresponding image in the second half of the batch. Okay, so if we construct our batches in this way, we don't need to know what the absolute image quality of any of these images are. Okay, because we know that whatever the network outputs, it better output a higher number for this image than it does for this image. Okay, in other words, the network should learn to rank these images in terms of image quality. So how do we ensure that we have this ranking relationship, that is respected in the batches that we construct? Well, for image quality assessment, it's kind of easy to do this because we can synthetically generate training data. If we have a high quality original image, okay, and any one of there's about 30 standard distortions, well, what we can do is we can take the original image and we can start distorting the image with Gaussian blur, in this example here, with different levels of different degrees of blurring. And we don't know what the original quality of this image is. We don't know what this image is, but we do know one thing for sure. The quality of this image is at least the quality of this image or less, because it's more distorted. And the same with this. We know that this image is at least the same quality as this image and the same quality as this image or less, because it's more distorted. That's the main idea. So if we denote the output of the network by C hat, okay, and we assume that the image I sub I is higher quality than ij, okay, whenever we have the index I less than j, we can use a ranking hinge loss defined like this as our proxy. Okay, so what we do, what we want with this is we want that the network output, okay, represented by the C hats here, respect the ordering. Okay, respect the ordering that the image quality of II is higher than that of J, which is exactly what this says. And the order should be respected, okay, to within at least a certain margin epsilon. So the nice thing about a loss like this, right, is that when we go to compute gradients over this loss, okay, we can first of all decompose the loss into these two components here, because if we respect the margin, then the loss is going to be going to be 0. Otherwise, we can distribute the gradient over the network outputs and decompose the loss into this difference between two gradients. Okay? So if we carefully construct our mini batches so that we always know this relative quality ranking, this exact quality ranking here, we can calculate the gradients in backprop away. Okay, so this is actually a technique that is used in contrastive self-supervised learning very frequently. So you carefully construct your batches so that you can put together the pieces of your loss together using and making the most out of each batch that you pass through the network. Okay, so after we train the network to rank in this way, we use a small labeled training set, okay, to calibrate the outputs of the network using just a simple squared loss. So we performed experiments on the two principal image quality assessment data sets at the time. We use a VGG network, okay, which is already pre-trained on ImageNet, okay, but as we show in the results, pre-trained on ImageNet doesn't really get you all the way. In fact, the self-supervised training it contributes significantly. So how do we determine if our self-supervised loss is actually learning something about the semantics? In this case, the semantics that we're interested in capturing are not object semantics of the image. Instead, what we're interested in capturing are the semantics of image distortions. And here what we have are 5 different types of distortions. Okay, sorry, we have one type of distortion. I don't remember which distortion we used in this image, and 5 different degrees of this distortion. Okay, and so what we can see here is that there's some overlap, and some of the distortions aren't really compactly estimated, the degree of the distortion. Okay, this would be the one corresponding to the 0 degree here, but they're fairly well separated. So what this indicates is that the self-supervised loss, the self-supervised training signal that we're providing, is learning something about the representation is capturing something about the distortions. And this is an illustration of how the fast Siamese backpropagation, which is technique of backpropagation that is exploiting this decomposition that I talked about here. This shows how we converge significantly faster on a better solution by using this, as opposed to using standard pair sampling in Siamese networks, so random pair sampling, or even compared to hard mining of pairs. Again, the us versus them, I'm definitely not going to go into these, all of these details. But one of the things that we established in this paper is that this is the first approach. Okay, this is a few years ago by now, and the state of the art has been significantly advanced since then. But this was one of the first approaches that, by using self-supervised learning, was able to achieve state-of-the-art results that exceeded the state-of-the-art results for what's known as full reference image quality assessment. So full reference image quality assessment is image quality assessment. It's the same problem, but where you have a reference image, high quality reference image, for comparison at test time. Okay, so it's a much simpler problem. So the moral of this story is that self-supervision significantly helps to improve the results, and self-supervision specifically designed for this niche problem. Okay, so let's look at a completely different application of exactly the same idea. So some of you might ask yourselves, and others have asked, well, this self-supervised learning by generating degraded versions of high-quality images, isn't that just data augmentation? Well, yes, but also no. Because in data augmentation, one of the things that we know is that any augmentation that we apply preserves the target output of the network, the class label, for example. But in the case of self-supervised learning, when we augment or when we degrade images, we're not preserving the output. In fact, we know that it's changing. Okay, we know that the image quality is going to be less. So it's really is self-supervised learning and not just data augmentation. Nonetheless, let's look at a completely different application of the same idea, where the construction of the proxy task needs to leverage the nature of the underlying problem. And this is the problem of dense crowd counting. And this is another example of an application where image annotation is extremely tedious, expensive, and as a consequence, the available data sets typically have a few hundreds or a few thousands of annotated images. So again, in this case, if you're interested in the details, I encourage you to go and look at the video on the workshop website, because I'm going to introduce the main ideas really quickly and then jump ahead in the interest of finishing in some approximation of on time. So how can we derive a proxy ranking task from the nature of crowd counting? Well, the intuition is quite simple to understand. So if I have an image, and I don't know anything about the image except that it contains a crowd of persons, and I start sampling images, okay, sub-images of this original image that are always contained within other sampled sub-images. Well, I don't know how many people are in any of these images. Okay, but I do know one thing, well, two things for sure. I know that the number of persons in this image, the central image here, is less than or equal to the number of persons in this image, because it's a sub-image of the green image patch. And the same for the green image and the yellow image with respect to the red. Okay, so whatever the network outputs for this, I don't know what its absolute value should be, but I do know that it should be less than or equal to whatever the network outputs for this image. Okay. So from this observation, and by carefully constructing batches, we can construct a ranking proxy. So one last detail before I move on. In this case, we need to be really careful about what the network is actually estimating, because remember, the network can and will cheat if it finds a way. And in this case, for example, if the network always outputs 0 as a count, or something that's proportional to the number of original image pixels in the sampled patch, it will trivially respect the ranking loss that we're applying to it. So what we need to do is we need to make sure that whatever the network is counting, or ranking rather, because it's not doing any counting yet, is semantically relevant to the task that we want to, the downstream task that we want to solve. Namely, that it's counting some features that are related to the presence of persons. So rather than use some sort of a contrastive loss using different images and having sampling triples, maybe, what we did in this work is we instead use a semi-supervised loss in the form of a multitask network. So we construct batches to have a combination of labeled images, ranked images. We pass them through the same network architecture to represent some output density map, and then the labeled images are passed to a supervised loss, whereas the unlabeled images that we can only rank because we know how the images were constructed by subsampling, we pass through the proxy ranking loss, exactly the same one that is used that I described for image quality assessment. And so this multitask network simultaneously learns how to count persons in images, and it uses unlabeled data in order to improve its representation, right, via this proxy ranking loss.
All right, so for the first talk, I want to pause it here. So I encourage everyone, if you're interested, please look at the full video on the workshop website. And very quickly, is there any question for this talk so far? Because Professor Baghdadov is online with us now. Please voice out the questions if you have any.
So this is Terry. I have a question. For the ranking loss, have you looked at any problems where you don't know exactly, you know the ordering, but the ordering is sort of like a convex function, it goes up and then comes back down, as opposed to having a strict ordering?
That's a really good question. So the short answer is no. We haven't looked at that specifically. We did look at some at different ways of combining sampled patches in terms of looking at the relaxing the requirement that they be that the sampled images be proper sub images of other ones, and so the intersection of the two images was used to form a sort of a inclusion exclusion algebraic loss, which would be probably similar to what it is that you're talking about, but we didn't really get very far in looking at that. So again, the short answer is no, we didn't really look at that, but it seems like something that could be quite reasonable and probably would be useful, as long as there's some downstream utility that is being expressed by this type of non-monotonic relationship.
Thanks. So a second question, you talked about a number of the different techniques. I'm just curious if how you consider the clustering based techniques, which are not contrastive, because you're really just trying to take the images and form clusters and whatever, something like deep clustering as a feature representation. How do you see that fitting within the sort of predictive models that you're looking at?
That's actually a good point, because that's not something that these techniques are not ones that fit neatly into this predictive versus contrastive dichotomy that has become the standard way of describing the status quo of self-supervised learning. I guess I haven't really thought about this, but I guess I might think I might consider them generative techniques, since in some ways, if the clustering models if you squint, you can think of them as being generative models in some sense, and I'm not sure if that is groupable into the predictive category of techniques, or if that's really a proper a proper category on its own. I guess it would be a proper category on its own if I thought about it. But that's an interesting question, the one that I haven't really thought about. And I'm not aware of other generative ones that use, let's say, more explicitly generative models for self-supervision. I'm not sure if this really addressed your question. It may, I think it created more questions for me than anything else.
So I'll let somebody else ask questions. If not, I do have another, but I'll let somebody else ask first.
Is there any question? Any other question? If not, for the sake of the time, I'm going to play the video of the second talk. And thank you very much, Andy. Nice talk. And if you have any further questions, feel free to reach out. And to me, I'm happy to direct the question to Professor Beckmendorf, or you can directly reach out to him. Thank you so much again. Yeah.
Great, thank you.
The second talk is given by Professor Seeslook from
Welcome everybody. My name is K. Snoek. I'm from the University of Amsterdam. Today I'm going to talk about debasing algorithms for images seen and unseen. And this is joined in a topic of Amsterdam. Today I'm going to talk about debasing algorithms for images seen and unseen. And this is joint work with William Tong, who is a PhD student in my team. Bias has been a topic of increasing attention in our community. And although it has been known for quite a while, so this is probably one of the first papers on the topic by Toralba and Afros, where they identified that different data sets in the vision community have a certain bias, to the extent that based on sampling a simple single frame from each of these data sets would already give you a very good indication where it originates from. So they even provided a short quiz in their paper where the readers were asked to identify, well, does this image belong to Pascal, Label Me, ImageNet, or the Sun dataset? And because most datasets were relatively small at the days, some researchers could even identify individual images. So they would know what images belong to the airplane category in Pascal, for example. And well, problem with such a bias is that learning an algorithm on the one domain would not generalize to the other, which is also an active area of research at the moment. Looking into dataset bias a little bit further, there was a follow-up work from De Vries et al., who looked into geographical bias of large image collections. So here you see some examples from ImageNet, Coco, and Open Images, where they have figured out what is the origin of the different images by using GPS coordinates, and what is the distribution all over the globe. And then if you compare this distribution with a general density map showing a world population density map, there is a big mismatch. So where the existing vision datasets have a strong bias in either the USA or in Europe, that is not necessarily also the most densely populated area in the world. So if you look here into Southeast Asia, one of the most densely populated areas in the world, it's largely missing from datasets like Coco and ImageNet. What kind of problem does this create? Well, a wedding in the Netherlands looks quite dissimilar from a wedding in India. So by not feeding your algorithms data from a large variety of how things look in the world, they become biased too. So another example is spices. So the variety of spices in Iceland will be different from the variety of spices in Sri Lanka. So you want to really make sure that you cover the entire globe, so to say. Another example of dataset bias is skin color bias. So this plot shows essentially a global distribution of skin color and how it is distributed over the globe. So it is, of course, well known that most Africans have a darker skin, while those from Nordic countries are lighter skinned. Now, what the researchers found in this case is that existing face recognition algorithms did not really take this skin color distribution into account, and they have a very strong skin color bias towards white males. So what this means is that all they did an evaluation with several face recognition classifiers, including commercial packages, and they found that they perform best for lighter individuals and males overall, and no matter what classifier was taken, they performed always worse for darker females. So this is, of course, a bias that you don't want to have either in your dataset or in your classification algorithm. Now, this is not purely a computer vision problem. So this is a plot from another paper from Garg et al. That appeared in PNAS. And what this shows is bias in text corpora, most notably as captured in a word-to-vec embedding. So what they did here is they used the standard Google News word-to-vec vectors that are trained on the Google News dataset. And you see some interesting behaviors here that occupation of women is especially trying to emphasize those activities like being a nurse, a librarian, or a dancer, while carpenters and engineers and mechanic is much more rare in these data sets. So this gives us, again, a very unwanted bias. So what have people done to mitigate this bias? There are several tactics. So one is approached by Timur Gibro et al., where they worked on what they call data sheets for data sets. And data sheets are commonly used in the electronics industry, where every component, no matter how simple or complex, is basically accompanied with a data sheet that describes how it is operating, what test results, recommended use, and what have we. So they took this as an analogy and then basically also proposed to equip data sets that people come up with also with such a data sheet. And this dataset can document the motivation for the dataset, the composition, the collection process, intended use, how it is distributed, who is maintaining it, and so on. So this facilitates better communication between the dataset creators and also the consumers of this dataset. So they know also what is the intended use, how was it set up, what are potential biases that result from the creation process. So this provides trust, transparency, and also accountability for the dataset and its creators. And most of all, it raises awareness. So this is very important development. Another way to mitigate dataset bias is by taking existing dataset and filter it and balancing it or correct it so you wish, to better have a better balance overall. So here you see an image I took from a paper by Young et al. That appeared in Fact last year, where they show the distribution of images in the ImageNet scene set for programmer before and after balancing to a uniform distribution. So the top row shows the original sample for programmer in ImageNet, and then the next row, so after balancing it for certain attributes. So when balancing it for gender, you will see more female programmers, for example. And when balancing for skin color, also darker skin colors are better represented in the sample. And last but not least, they also accommodate for age variation. So this is a good way to mitigate dataset bias, be it that it requires a lot of additional manual labor to redo the initial labor, so to say. Then there's also methods that can do some automated analysis, and this is a paper from Wang et al. From ECV 2020, where the authors have proposed a tool that takes as input a visual dataset and then and its annotations and outputs metrics which seek to produce insights and also possible actions. And here you see some examples for the COCO dataset, where people, so insights they could compute automatically are things like object counts and duplicates, and they could take into account object scale. And what can you do with that? Well, basically you can automatically extract from the dataset and the label that, for example, the super category appliance within that category, oven and refrigerator are overrepresented, and toaster is underrepresented. So a possible action could be to query for more toaster images and to sort of like expand the dataset on this particular category. In terms of object scale, you could extract that airplane is overrepresented at a very large scale in images. And there are only very few images of airplanes in smaller scale and flying in the sky. So this again provides a means to supplement the dataset to better mitigate bias. So far, all these examples have emphasized bias in datasets. But there's also bias in algorithms. And this was an interesting discussion going on Twitter. And the trigger was the figure you see over here. And clearly on the left is a downsampled image from former President Barack Obama. And here is a generated results that sort of try to create the alternative figure in a better, higher resolution. And there was a discussion whether this was a problem of dataset bias in the dataset or bias in the algorithms. And there was a nice discussion between Jan LeCun, who was in the dataset side of things, and Timothy Gebru, who was more said, oh yeah, it's not only the dataset, it is also the algorithm. And I think Timothy is right. Dataset is an important source of bias, but algorithms are biased too. So here's a paper from Zhao et al., where they had an interesting observation. So they were looking into the in situ dataset, which is about visual and semantic role labeling. And they found that in the training set, 33% of the cooking images have a man as in the agent role, while the rest have a woman in the agent role. So it's already an interesting bias by itself. But after they trained a conditional random field, the bias was amplified. So now all of a sudden, in the test set, man was only predicted in 16% of the cases for the agent role. And in all other cases, women were given the preference. So they proposed a method to correct for this amplification. And after applying their methods, they could correct for this bias in the CRF algorithm. So we got inspired by this work. And in this talk, we will also talk about mitigating algorithmic bias. And in particular, we will focus on many zero-shot image classification algorithms. So in part one, we will talk about debiasing algorithms for images seen. So this is the many-shot scenario. And in part two, we will also consider the zero-shot image classification problem. And both parts are based on two existing papers. And rather than me presenting them in detail, I figured it is much better to have the leading author present both works. So I would now like to give the floor to William Tong, who will present the rest of this talk. Thank you.
In terms of accuracy. In this paper, we pursue an analogous reasoning from embeddings, from word embeddings, and reveal that biases are also implicitly present in image classifiers. And we propose methods to mitigate biases during training and also as a post-processing step while maintaining a high accuracy. It's also important to note that biases cannot be removed entirely, as they can still be recovered to some extent, as it has been shown in the literature. So we mainly mitigate biases rather than producing a completely debiased model. To reveal a bias direction in the feature space of image classifiers, we propose to compute class-specific prototypes. Imagine that you want to classify images of cats, dogs, and frogs, and that these images can either be in color or in grayscale. So the idea here that we propose is to compute the average feature representation for colored cats and for grayscale cats, and so on for the other categories. Once all the class-specific prototypes have been computed, we can derive the differences, delta, and we do so for all the classes that are present in the data sets. What we observe is that when applying a principal component analysis of the class-specific prototype differences, we observe bias direction. So on the left here, we can see that there is a main direction of variance in the principal component analysis of delta. And this actually corresponds to the color bias direction, so the color and grayscale difference. And to verify whether this main direction of variance actually corresponds to the color bias direction, we also compute the principal component analysis on a random delta, where we match randomly specific prototypes and disappears, which is illustrated by a much lower skewness in the distribution of the principal components. Interestingly, this result corroborates with related works in word embeddings, in which the authors also find that the bias is encoded in the main direction of variance. To mitigate such bias, we propose to map images to domain-specific embeddings, where each protected attribute value has its own embedding. In this paper, we consider binary protected attribute values. For example, if the protected attribute is the gender, then we consider female and male values. We would like to stress the real protected attributes can be non-binary and to binary protected attribute values. So given an image X, we learn a convolutional neural network to produce a feature representation H, which is further mapped to its own embedding space to get Z. And if the image X belongs to the attribute value 0, then we map it to its we map it to its corresponding embedding space Z0. And to learn such an embedding space, we rely on a cosine softmax formulation, where the idea is to regress the embedding representation to a corresponding latent parameter W. This regression problem is then turned into a classification one by applying a softmax function, and learning is done by minimizing the negative log likelihood loss function. Such formulation, so having a cosine softmax formulation, has notably been shown in the literature to yield a greater class separation than the traditional softmax formulation. And this is a property that we will exploit to mitigate biases. During training, we are given the attribute value label. So if the image belongs to attribute 0, we will only update the parameters of the head 0. And we will ignore the other head that belongs to the other attribute value 1. And during testing, there's no attribute value label, of course. So we simply average the predictions over the two heads. So we average the results that are coming from Z0 and Z1. Once trained, we can actually apply also a post-processing step, and we propose a post-processing step to reduce even more the bias effect that consists in computing class-specific prototypes and remove the main direction of variance in the feature space. This operation is illustrated here on the right. So the idea is that we first project the features H on the bias direction B to obtain HB here. And we mitigate H by removing HB from the features H. In the end, we get H tilde, that is the representation that corresponds to mitigated features. In addition to measuring the performance of image classifiers with accuracy, for example, we also report metrics to measure the fairness of the predictions. In particular, we are interested in the bias amplification between training and testing sets. And the idea is to compare positive hits of the model for every class and check if this is similar to the training set statistics. We also measure metrics typically used in the fairness literature. The demographic parity looks at the independence between the prediction and the protected attribute values and check if the model produces positive predictions for both protected attribute values. The equality of opportunity looks at the conditional independence between the prediction and the protected attribute values and check the recall, or sometimes called the true positive rate, of the predictions for both protected attribute values. For the evaluation, we rely on the benchmark initially proposed by Wang and his colleagues. We evaluate in two settings, a multi-class classification setting with a skewed version of C410 and a multi-label classification on Celeb A. Note that all baselines use the same backbone, optimizer, and hyperparameters for fair comparisons. Before jumping into the benchmark comparisons, let us gain some insights with evaluation studies on Celeb A. First, we assess the effect of having domain-specific heads. We define two scenarios for a single head that we compare with. One where every class is represented once, and another one where every class is represented twice, once per domain. And we observe that our domain-specific head here outperforms both single-head scenarios overall. Although the single head with multiple class representations is better in reducing the bias amplification, its performance in the other metrics is quite bad because mixing two losses, one for each protected attribute value, in one single head creates confusion in the model. Second, we assess the effect of having a bias removal post-processing operation. And we observe that removing the bias direction in the feature space helps in the fairness metrics here, but causes a small drop in the attribute prediction task. In multi-class classification, we compare our method with several alternatives. And the evaluation is done on a skewed version of a C410, where 5 classes are biased towards color images, while the other 5 classes are biased towards gray images. The baseline is a standard ConvNet, and it can be extended with an oversampling operation to sample more, so to show more to the model underrepresented attributes during the training. So this helps if we look at all the metrics here to improve the performance, but also to reduce a little bit the bias effect. Adversarial creates a domain invariance in the feature space. So the idea is to have an adversarial loss on the feature space such that the feature space cannot distinguish between grayscale and color scale images. And interestingly, when looking at the results of adversarial, this is actually the worst method. The adversarial loss removes the discriminability in the feature space and does not help to make a prediction fair either. which is kind of counterintuitive because the goal of the adversarial loss is to actually blur the distinction between both protected attribute values and then get predictions that are more fair. Domain discriminative creates a class for every category and domain pair. For example, a colored cat will be a class and a gray cat will be another class. So this simple solution is actually quite compelling as it outperforms the previous ones. Our method is most similar to domain independent, which also creates domain-specific heads. We mainly differ by the usage of a cosine softmax loss function and the additional bias removal operation. Overall, we improve on the fairness metrics, while there is still a little gap in performance in the accuracy. We also evaluate our model on multi-label classification. For this benchmark, Celeb A is used. The task is to predict the presence of 39 binary attributes, and we report the mean average precision score. The conclusions from the multi-class classification also apply here for the multi-label classification, where our proposed model improves on the fairness metrics, but at the detriment of a small drop in the MAP score. To wrap up, in this work, we reveal that biases are implicitly encoded in image classifiers. And to mitigate the effect of such biases, we propose domain-specific embeddings with a bias removal operation on the feature space. Evaluation on both multi-class and multi-label classifications has shown their benefits to produce fair predictions. I will now present our work that focuses on debasing algorithms for unseen classes. This work was accepted earlier at BMVC last year. Our work focuses on mitigating the bias towards the seen classes during training in generalized zero-shot learning. The objective of generalized zero-shot learning is to train on seen classes, the blue dots here, and to test on the joint set of seen and unseen classes, so both blue and red dots. One of the main challenges in generalized zero-shot learning resides in an inherent bias present in classifiers. For example, when showing an image of an unseen class to the model, say this image here of a jaguar, it will most likely land close to a seen class representation. So in this case, it might land close to the cat representation. A bias then appears during the evaluation phase, as probabilities of classes seen during training tend to be higher. In this paper, we propose two mechanisms to mitigate this bias. First, we make the model more confident with temperature scaling, such that the image of a jaguar lands further away to the cat representation. And second, we regularize the entropy of class probabilities, such that the image of a jaguar yields higher unseen class probabilities and lower seen class probabilities. Models for generalized zero-shot learning have initially been trained with only inputs from seen classes, and as these previous methods result in a low accuracy score on unseen classes, the current approach is to generate features for unseen classes. So the idea is to use a generative model, for example, a GAN, a cycle GAN, or a VAE, to generate features that correspond to unseen classes. In this paper, we design a classifier that operates in both settings, so with only seen class inputs, but also with the addition of generated unseen class inputs. As mentioned in the previous slide, there is a bias towards classes seen during training, and actually all classifiers are affected by this inherent bias, whatever the setting is. So far, only a few works try to address it by treating seen and unseen class predictions separately. And in this paper, we rather incorporate mechanisms to balance out seen and unseen class probabilities jointly. We formulate the generalized zero-shot learning problem as a mapping between the input features to the class representation. So in this case, the model maps the image of a cat. So actually it maps this image here, for example, of a cat with the function f that will project it to an embedding space to its semantic representation, phi of a cat. So typically the class semantic representation corresponds to a sentence embedding. So a sentence to describe what a cat is, or an attribute representation that is a set of binary values to describe properties that are present or absent in a cat. Next, we apply a softmax function to have a probabilistic model of cosine similarities, and we then incorporate a temperature scaling mechanism to calibrate the predictions of the classifier. This formulation works for the setting with only seen class features, as shown here in this equation, and can easily be extended to the setting where generated features for unseen classes are also present. The only major difference between this equation and the previous one resides in the partition function, such that we can still learn from seen examples and also from generated unseen examples. So the partition function here includes both seen and unseen classes. When generated features are available for unseen classes, we can go one step further and regularize the probabilities. Intuitively, we would like the entropy of the seen class probabilities to be high in the presence of an unseen class sample. So for example, here, if we show an image of a jaguar that corresponds to an unseen class, we would like the entropy over the seen class probabilities to be high. And the reverse, when we show an image that is coming from a seen class, so here a cat, we would like the entropy of seen class probabilities to be low. We then derive a margin-based formulation to minimize ring training. We can also do the opposite for the unseen class probabilities and consider the entropy over these unseen class probabilities. The evaluation is done on standard datasets for generalized short learning. We rely on 4 common datasets that are CUB, SUN, AVA, and FLOW. CUB is for fine-grained bird classification, SUN for scene classification, AVA for animal classification, and FLOW for fine-grained flower classification. We follow the common setting in the literature that is made for generalized short learning. And specifically, we use features and sentence representations already extracted by Qian and his colleagues, and do not fine-tune the backbone network or the RNN network that is used to get sentence representations. And we report the harmonic mean between seen and unseen accuracies. Before jumping into quantitative evaluation, let us present the effect that we want on the predictions by mitigating the bias towards seen classes. So consider this example that is taken from the AVA dataset. So this is an image of a bobcat that corresponds to an unseen class. When we show the model this image of a bobcat, what happens is that if the model has not bias awareness, top predictions will mostly come from seen classes. So we can see here that when looking at the top 5 predictions, most of them are blue, so they correspond to seen classes. And thus, this will most likely yield a low performance. Instead, what we want is that with bias awareness, the model knows that the image comes from an unseen class and thus ranks unseen classes higher. So here we can see that all the top 5 predictions correspond to an unseen class. So predicting the true class label becomes simpler, which in return improves the performance. When looking at ablation studies and when analyzing more closely the bias towards seen classes, we find that the bias actually varies across datasets. So in other words, both datasets and models are biased, and also not all datasets are affected to the same extent to the bias towards sin classes. Further ablation of the two proposed mechanisms show that setting the temperature to 0.05 is best to ensure the confidence of the classifier during the evaluation phase, and that the regularization should be applied to both seen and unseen class probabilities, as doing it only in one direction can negatively affect the results. In this work, we also rely on a real value representation space. So remember that we map images to embedding space that correspond to the class semantic representation. It then enables us to swap class representation to less biased representation. We may have, for example, a biased representation that is interpretable, like attributes, and another representation that is less biased but less interpretable, like sentences. So we can actually mix and match those two to have an interpretable prediction, but also with a high performance. So this is an example on the CUB datasets. And in this scenario, it would be interesting to train on attributes and use sentences for evaluation. Going from one representation space to another one can simply be done with linear regression. So here, the attribute and attribute setting, as well as the sentence and sentence setting, is the non-swapped setting, so the normal one. And we can see that sentences produce higher performance than attributes. Then we have in the middle here, those two that correspond to the swapped setting. We see that sentences used, when we use sentences during training and attributes for the evaluation, this is less effective than the reverse because it requires a dimensionality expansion from the attributes to the sentence embedding space that is much higher, that has a much higher dimensionality. Finally, here are some state-of-the-art comparisons with two other classifiers, namely the one-hot softmax and the Cosmo classifier. First, it is worth noticing that the two other alternatives, so the one-hot softmax and the Cosmo, are not standalone. This means that they cannot operate with only seen features. They need a combination of seen and unseen features to be able to learn to classify images. Second, our bias hour classifier is compatible with any type of generated features. And as such, we evaluate on features coming from GANs and also cycle GAN, where we achieve state-of-the-art results on the 3 most biased datasets out of 4. And we also expect even bigger improvements by incorporating the features coming from more recent generative models. To wrap up, in this paper, we propose a bias-aware classifier that is based on 2 mechanisms. First, we calibrate the predictions with temperature scaling. And second, we regularize the entropy of seen and unseen class probabilities jointly. Our formulation can be used in a setting where only seen class features are available, but also in combination with generated features for unseen classes. And this can be done for any type of generative model. In conclusion, we would like to emphasize in this talk that biases should be considered during the training and also during the formulation of the problem task to avoid any potential adverse decisions. Indeed, biases are present in both datasets and algorithms. This will definitely impact the fairness of the predictions, and we then need to be able to identify these potential harms and design strategies to mitigate them during the model training. More particularly, in this talk, we presented methods to mitigate biases in classifiers when all classes are seen during training, but also when there is an evaluation on unseen classes. This concludes my presentation. If you have any questions, feel free to contact Case or myself via email. Thank you again for the invitation, and thank you for listening.
All right, so that's the second keynote talk of today's workshop, and then we will take a short break until 10:50 a.m. PST, about 20 minutes later, and we'll be back to start our third talk from Professor Ehsan Elmhafar from Northeastern University. And yeah, so let's take a short break.